Hey, this is Bill. Lesson 4-2 is our next one here. It's horizontal and vertical lines. You need to read through this to find the information in there. The basic idea is a line that is parallel to the y-axis and perpendicular to the x-axis is a line that is where x equals some constant value. A line that is parallel to the x-axis and perpendicular to the y-axis is a line where y equals some constant value. And this is shown in the examples that we'll come to in this lesson, and I'll get to that in a minute. Just want to review what's in here. There's a couple of vocabulary terms that you should know about, followed by the equation for a horizontal line, which says every horizontal line has an equation of the form y equals k, where k is a real number. So k is some known number, in which case y is always that value. In example 1, if you look at the graph to the right, you see an example of a y equals k line. You'll notice that that line is parallel to the x-axis. It is perpendicular to the y-axis, but anywhere on that line, for this particular problem, y is equal to 2. Y is equal to 2. X can be anything, but y is always equal to 2 along that line. The equations for a vertical line: for every vertical line has the equation of the form x equals h. Again, where h is a real number, so it's some number that we know. We see to the right a graph of an x equals 4.5, 4.5. We see that that line is parallel to the y-axis and perpendicular to the x-axis, but anywhere on that line x is equal to 4.5. Y could be anything. So you want to go through these examples. I'll have a couple others for you. We have patterns that evolve from horizontal lines, and we can use those sometimes to find the intersection of two graphs, one which is the solution we're interested in getting. The other one is the graph of a linear equation, a line that's not horizontal or vertical. And we can use that to pick off on the graph an intersection that we could use to answer a problem. We'll get to the deviation from the mean. There's an activity involved, and so I will walk you through that. This is making use of the idea of a horizontal line where y is always the same value, which is the mean of a data set, and comparing the data to that mean is one use of a horizontal line. Your assignment is covering the ideas and applying the math. There's definitely some graphing in this one. Again, remember to use your ruler, use graph paper, do this neatly, do it completely. Looking forward to hearing if you have any questions and also seeing how you do on the mastery quiz. I will carry on with some examples in just a moment. Going through some extra examples here for lesson 4-2. First, I want to look at this whole idea of equations of the form that we've been talking about, where we have this strange thing moving around. Go away. All right. So if I get an equation where it says that x equals 2, well, what does that mean? If it's a number line, then it's just a point on the number line, right? I mean, we know that from our work with number lines. And so I'll put my 0 there. 1, 2, 3, 4, 5. 1, 2. So that's -2. This is 1, 2, 5. And so we know that x equals 2 is this point right here. And the question becomes, if I have an equation of the form x equals 2, when is it just a point versus when is it a line in the Cartesian coordinate plane? And answer to that is if I'm dealing with equations where I am dealing with two-dimensional situations where there is an x and there could be a y, then I'm into the Cartesian coordinate grid and I have to graph that accordingly. If I was going to look at that in terms of what it would look like, let's just make a quick graph, shall we? Ooh, that's really bad. Now let's make a quick graph. Okay, and we go in here and we make some tick marks. If you have graph paper, it's so much easier because you can be really accurate with it. This is our y-axis. Here's our x-axis. Okay, so I just wanted to get a basic graph in here. Need some arrows on the end to indicate that these axes go forever. And now we've got something where we can go in and make some plots. So if I have my x equals 2, I know that here's the x number line, here's the y number line, and they cross each other. Where they intersect is at 0, 0. And if this is 1, and then this is 2, my x equals 2 is going to be right here. So that's going to be part of this plot for sure. It has to cross there. But if I have x and y in this two-dimensional sense, x is always going to be 2. Always. I could keep going. So this is always 2. What could y be? Well, because it's a vertical line, y could be anything. So in our first case, it's 2, 0. In this next one, I'm going to pick another number. I'm going to make it easier for me. Easy because I've got my graph the way I do. I'm going to make this 4. And I'll make the other one -4. These are all possible points for the equation x equals 2. So I've got this point here at 2, 1, 2, 3, 4, 2, 4, 2, -4, and if I got my lines nice and straight, I should be able to make a line that'll go through all of them. Yeah. Use a ruler. So here I got my vertical line, and that's what it represents. Now I could do this in set builder notation. Let me clear some of this out of the way. Okay, so I've got that out of the way. If I was going to do this in set builder notation, then I'd be looking at something like this. Our original equation was x equals 2. Set builder notation, remember, is this. It's x, the set of all x, such that x equals 2. Okay, now if I was to write it like this, then what I'm saying is this is on a number line. So this is the number line x. Okay? If I was to write it this way, the set of all x, such that set of all x, y such that x equals 3. Now this one, because it's a set of all x, y such that x equals 3, is saying that x is always going to be 3, and then y is anything it can be. It's anything else. So this is a set builder notation, and this would be a graph, two-dimensional graph. So we've got two different conditions. You've got to get it sometimes out of the context for the problem and see if that will help you to resolve it. Okay, we're going to carry on with some more graphing examples here now that we're moving away from the basic description. So I've got a graph for you. Let me pull this up. And the question is, what is this the graph of? What's the equation for this graph? And one way to evaluate this is to just look at, well, one, is it a horizontal or vertical line? It looks to be horizontal. If is that, then for this, what are the possible values? So if x is, well, let's look if x is 0. Make our little table, x, y. If x is 0, then what's y? And make that look more like a y. What's y? No, y is -3. And if x is -5, then y is -3. So I've got a couple of those as it passes through -3 on the y-axis. That's the y number line, and so that means this line represents the equation that we're interested in, which would be that y equals -3. So we can see that from this, we can pull that out, and we get that that's the case for this. Okay, let's try graphing something ourselves, shall we? So we'll pull this out. Got a graph. You should have some graph paper as well. And I'm going to do two things with this one. One would be to just graph it on a number line, and two would be to graph it on the coordinate plane. So we'll first look at this graph on the number line. And the equation we're looking at is, let's see, x equals -15. All right, we've got the x equals -15, and we want to graph that first on a number line, and then we'll graph it in the coordinate plane. So first we need a number line, so we'll lay one in here, and this is the x number line. Got some arrows on the end. We've got kind of our 0 here. So if this is 0, this will be -5, -10, -15, -20, and that's 5. I'm going to go by 5s, and so at -15 is my point. This is the x equals -15 on a number line. So we can do that. I think we've seen that before. Now let's look at graphing x equals -15 in a Cartesian coordinate plane. So we'll pull up a plane, and we've got, this is the y-axis here. Here's our x-axis. We need a scale for this. Well, I'm at -15. So if I go by 1s, I'm kind of run out of room here. I could go by 2s. I could do what I did before, maybe go by 5s. I think I'm going to go by each tick being 2.5 to kind of give myself a little bit of room to work with. So let's see what that's going to look like. So this is x equals a negative 15, so that's what I'm interested in. So this is negative 5, so that's negative 10, negative 15, negative 20. And this scale could be different. This could be 1, 2, 3, 4, 5, negative 1, negative 2, negative 3, negative 4, negative 5. The x scale is the same. So that's 5, 10, 15, 20. So now I've got it scaled, and I want to go in and put my mark in. I know my equation was x equals negative 15. So I know that negative 15 is one of the points. And I know this is going to be a vertical line. It's because it has to always be negative 15. No matter what x is always negative 15, and then y could be anything else. So if x is a negative 15, y could be 5. That's a solution. So now I can see that anywhere along this vertical line is a place where x can equal a negative 15, and the graph for this line will run along here. It gets arrows on the end to indicate it goes forever, and now I have the graph for x equals a negative 15 on the coordinate plane. Okay, this is a continuation of the 4-2 extra examples. This is our third example, and this is similar to example 3 in the textbook. So Ricky's taken $1,400 with him to college for spending money. If he spends $100 per week, how many weeks will his money last? Well, we can graph this and find that information by looking for the intersection between the constant line, 1,400, and the linear equation, $100 per week. With that information, we could determine where the intersection and how many weeks his money will last. Now, some of you might look at this and you already know the answer. You figured that out. That's great, but go through the activity and the exercise to make sure you understand how to do this, so that when you don't know the answer, you know how to proceed in order to get it using a graphical technique. So we're going to pull up our grid here for graphing, and we want to kind of mark what's what. So we've got our x-axis, we have our y-axis. Now the convention here when we are determining which side to use for what is that time is typically the independent variable. Independent variable is usually the x variable. The dependent variable, y, is going to be what happens as time passes. Well, as time goes by, money gets spent, right? He's spending $100 per week, and so that would be dollars up there. So I'm going to go ahead and we'll mark, this is y, in dollars, y dollars, and then our x is in weeks. And now we got to figure out a scale that's going to fit into this graph. So I think what I'm going to do here for my weeks is I'm going to go by 200 per unit. And so that would make this 400, 800, 1200, 1600. Right? So I'm at, that's 2, 4, 6, 8, yeah. 4, 8, 12, and 16. Okay, and I think here what I'm going to do is going to go up by 200 at a time and see if that'll get me where I need to be. 2, 4, 6, 8, 12, 14, 16. Yeah, that'll work. I need to do something about this money or the question right there. So let me go ahead and get rid of that for a second. And so on our money scale, we're going up at, that's $400. So that's 800. That's 1200. So 2, 4, 6, 8, 10, 12, and that's 1600. So right here is 1400, and we need that. That's kind of our number of interest. So $1,400. Now we want to go ahead and make a graph of this. And so what he had to begin with was $1,400 that he was taking with him to college. And spending $100 a week. So we're going to bring our graph back up here and make Ricky's stuff go away. Okay, and so $1,400 is how much he's got. So we'll continue with our green color here. And what we're going to do with that is that 1,400, we're going to treat it as a constant. So he's got $1,400 there. We want to get a line that's going to extend out for us from 0. Put some arrows on that just because. And so this is this $1,400. This is the equation for y equals 14. $1,400. So that's that axis. Now the other thing we had is that he's spending $100 per week. And that $100 per week, it means that we have an equation that is y equals 100 times x. This is dollars per week, and x is in weeks. Excuse me. And so whatever number of weeks times that gives us how much money there is. We want to have a little idea of that equation. So we have our x, we have our y. If x is 0, it's the beginning of time, he hasn't spent any money. So at that point he has not spent anything, so y is 0. So remember, this is his spending. So next we'll go and we'll try, how about x is 8. 8 times 100 is 800. He's spent $800 by week 8. And this is what we need. We have this point at 0, 0. We have one at 800. And now we have enough information to draw a line and see what happens with that. So we're going to extend our line on up. We're going to assume, maybe like Ricky does, that he can spend forever. But now we've got a line we've drawn that is his spending line. This is the line for y equals 100. Still got my straight line tool on. 100x. So that's this line. Now what we're interested in all of this is the intersection of the two. We want to know when his spending line crosses his available money line. He has 1,400, which is right here. then what is the value, or what is the number of weeks down here? Because that was the question, how many weeks before he runs out of money? And we see we drop down and we're right here, and our answer is that he runs out of money in 14 weeks. So this is our graphical technique for solving this type of a problem. We could look at this as an algebraic problem, in which case we would start with 1500 or 1400, excuse me. So he had $1,400. He was spending, so decreasing this by $100 per week. And we want to know when he runs out of money. So when he runs out of money, how many dollars does he have? $0. And in this case, we want to solve for x. We know how to do this. This is the type of problem we've seen before. I'm going to make this plus a negative to help with the manipulation. I'll subtract 1,400 from both sides of the equation. So that tells me that a negative 100 times x is equal to a negative 1,400. I now divide both sides of the equation by a negative 1 over 100, or multiply by that. And I get then negative times a negative is a positive, x. Negative divided by a negative is a positive. Cancel out the zeros. I'm left with 14 weeks. So I get my answer algebraically. But we can use a graph to solve for this type of problem. Okay, remember covering the ideas, applying the math. Good graphs, use a ruler, mark things clearly, label your axes. I think that's about it. If you make a mistake, start over, regraph. If you're unsure about your graph, try plotting it in your graphing utility and see what that shows you. That may help you with solving that. I'm going to carry on with the activity for the deviation from the mean. Okay, 4-2 continuation. This is the activity and the deviation from the mean. You can read through this, but what we're trying to get to is finding out what is the mean temperature in Flagstaff, Arizona, and we want to look at how much it changes during the day. In other words, how much below or above the temperature is above the mean. So we find that the mean is 68.1 degrees, and we can then determine deviation. So when we were at 3 p.m., the temperature was 82.9 degrees, the deviation was 14.8 degrees. At 3 a.m., it was 52 degrees, so the deviation was minus 68.1, was a negative 16.1 degrees Fahrenheit. And if you look down, you can see the graph that has the mean line, which is a horizontal line. Y is always the same value, y equals 68.1. So no matter what time it was, that's the mean. And then the data set are the points that are put into place over the course of the day, what's happened to the temperature. So what is the equation on the horizontal line of the horizontal line that is graphed? Well, that's really this horizontal line is, since it's horizontal, its y is always the same, so y equals, and what it equals was the mean, which was 68.1. Okay, that's our first one there. What is the equation for the horizontal line? The second question is give the deviation from the mean at 7 a.m. and 8 a.m. So here our question is one of comparing it as we did in the early part of the example in the paragraph above. So at 7 a.m. it looks like the temperature is, I guess I'll go to the table, 64 degrees. So 7 a.m. it's 64. So we've got 64 minus 68.1 equals a negative 4.1 degrees. So that's our deviation at 7 a.m. What is it at 8 a.m.? Well, at 8 it's 72 degrees. So 72 minus 68.1. And that equals, let's see, 72 minus 68.1. That's 3.9 degrees at 8 a.m. So that's our deviations for 7 and 8. And so then for 3, it's asking for which 2 hours was the deviation plus 58 degrees. Plus 5.8 degrees. Well, what I want to look for here is initially what's going to be 68.1 plus 5.8, because when I subtract 68.1 from that, I'll get my deviation. So 68.1, and that puts us up at 73.9. At 73.9 degrees. Now at 73.9, I look down through the table. I find at 9 a.m. I'm at 73.9. Keep going. It got hotter, hotter, hotter. It's going to cool off. There it is. At, let's see, that's 4, 5, 6, 7. At 8 p.m., 2000 hours, the 20th hour, it's 73.9 degrees again. So for which 2 hours was the deviation plus 5.8? Okay, temperatures, the temperatures T are described by the interval. And so this is asking you basically what's the temperature range for this whole thing. What's the lowest temperature and what's the highest temperature? So we're going to look through the table here. And okay, 46.9, anything lower, not going to be there. Okay, so 46.9 looks like my lowest temperature. So that interval for this one is going to be 46.9, and that's going to be less than or equal to T, which is less than or equal to whatever the maximum is. And yeah, I was just underlining that real quick. So, so 46.9 is less than or equal to T, which is less than or equal to the highest temperature. Now that's going to be middle of the day, right? So 82.9, I don't have anything 82.9. This is the interval that describes our temperature for the day, and this is degrees. Okay. Number 5, the deviations d are described by the interval. Now this is the case where you want to know what's the maximum deviation, maximum and minimum deviation, and we determined the high and low temperatures, so we want just the deviation from those. So we're looking at this deviation for the low temperature. It was 46.9 minus 68.1, and that's equals to a negative 21.2. It's a negative 21.2. The maximum deviation was 82.9 minus 68.1, and that's 14.8. So we've got our deviations, and we could put this into this interval where it would say 68.1, excuse me, 46.9 minus 68.1 is a negative 21.2, is less than or equal to d, which is less than or equal to 14.8. The deviation is positive when h, the number of hours since midnight, is in the interval. So this is asking you when it has gone positive. At 7 o'clock, at 64, it's still going to be a negative deviation. At 8 o'clock, it's now at 72, it's going to be a positive deviation. So the deviation is positive when h isn't from 8 o'clock, and that goes on until 8 p.m. So 8 a.m. to 8 p.m. or 8 in the morning to 2000 hours in the evening. And those would give us our deviations. At 2100 hours, 68 is below 68.1 and therefore falls into the deviation. So here this would be 8 to 20. The negative deviation, you'll see that this is written with an or in it, is because we're now looking at going between these two. The deviation is negative when h is less than or equal to, and it's negative when it's less than or equal to 7, and it's also negative when h is greater than or equal to 2100 hours. So you'll notice this is not written as a biconditional, because this is an interval where you go from the beginning to the end and everything in between is included. Here you have an or statement because you have one set of data that's at one end of it, a break, then the other set of data. You'll notice that the inequality signs are pointing opposite directions. 8. The maximum deviation and the maximum absolute deviation are blank and blank respectively. Why is the minimum deviation not equal to the minimum absolute deviation? So the maximum deviation is the positive value, right? So that maximum deviation is going to be our 14.8. That's the highest value of deviation we had. Maximum absolute deviation, you remember, was we would take the absolute value of the deviation and get that, and that came out to be 21.2. Remember, we had that interval, and deviation gave us a negative 21.2. So the maximum absolute deviation is 21.2. So why are they different? Well, the maximum deviation is the maximum value obtained from the deviation. The absolute deviation, the maximum absolute deviation is the distance of a deviation from zero, and that's the negative value. That's why the two are different and have to do with how far apart they are. Okay, covering the ideas, applying the math. Sorry for the racket in the background.